Good morning, ladies and gentlemen. So let us start. Our course is almost done, but still there is last homework package to do. So today we will have supervised homework on the fourth package. As usual, I will explain the formulation in detail, and then we discuss the problem. Right. There will be two problems, and we will do it in turn. Next to it, what I want to say is on Thursday we will have the last lecture of this course about relativistic quantum mechanics. And then somehow we need to explain your homework, right? So next Monday, this time, there will be yet another session, which I believe is not scheduled. I will put an announcement, but anyway, it will be online to keep the scheduling simple. And there we will explain this homework in a week. Also, I will use the opportunity to talk about the course in general, to answer questions about examinations, everything. Let me give perhaps even right away the summary of what I want to tell you. The best way to prepare for examination and make you safe against any surprises with this examination. Well, it might be a trivial thing to say. The only way is to look at old exam papers. There's plenty of those. All exams are of very same difficulty. All exams have approximately the same structure. So please don't get surprised. Look carefully, take time to look at old exam problems. There's also crazy, from my point of view, crazy semester. So it is short. That's why we have homework in the almost at the edge of our course. Normally, the semester will end somewhere mid-June, and now we accelerate. Right. It says also for those who are not very confident, the rehearsal will be much earlier than usual, not in the end of August, but if I'm not mistaken, somewhere in the mid of July. For me, it's a nuisance. For me, it's very inconvenient. I'm going to be very irritated. This implies that I will have to invent two exams almost simultaneously. It's double work for me. So please don't expect that I make it easier because of that. Fine. With this, I guess we can start today's task. Let's talk about homework. And I will start with a problem 9. Problem 9, you still remember problem 8, and it was something about environment, something which we have treated in lectures number 10, number 11. This problem is also in this direction. Let me talk about this. Let us understand why. Formulation. Okay, there is a quantum dot, like in problem number, what was that, 6. with one electron, which can be, which is also kind of flat, but it's not circular dot. It's a parabolic dot, right? So it is confined in that plane, but in XY directions, the confinement is parabolic. The confinement is parabolic. Right, so how to describe the system? We could write Schrödinger equation, but after doing that much of advanced quantum mechanics, we have learned the better method. The better method, more efficient method, is just to write the states of this dot, which works for parabolic confinement only, in terms of bosons, in terms of bosonic creation and annihilation operators. So here it is. We have two oscillators corresponding to oscillations in X and Y direction. Good, and all states of the dot can be obtained from number states of these two oscillators. Okay, what was here? Just for convenience, coordinates of the electron are expressed in terms of these operators. Creation relation operators with a constant R. Then how about interaction with outside world? It is pretty much the same interaction as for atoms. We have already looked at it in homework and during the lectures. So this is interaction, and this is actually dipole interaction. So just, how do you call it, inner product of dipole vector and electric field. As to electric field, again, it's a field operator, which takes a form custom for electromagnetic field in vacuum. And next to it, we, of course, have the photon Hamiltonian. Photons are also bosons. And with specific spectrum. Good, so we have total Hamiltonian. Let us see. There are I would say the goal is roughly the same, but we reach this goal in different ways. The goal is to understand dissipation in this oscillator. It is clear that excited states of this quantum dot are not stable. They decay with emission of a photon. Right? So first of all, we use Fermi-Golden rule formula for that. We also concentrate on a specific excited state. It's a bit funny. Let me take time to talk about this. This state is a superposition of the two. So we have ground state of the oscillator, it's unique. We look at the next excited states. And we understand that we can induce oscillations in x direction and in y direction. And since the dot is circular, the energies of these two excited states are the same, precisely the same. This is degeneracy. As a consequence of this degeneracy, we can take as a first excited state any linear combination of the two. So look what I've done here. I excited either X oscillation or I oscillation, and I took superposition of the two. Okay, let's imagine the units A, B are real numbers. Good. So let's go point by point. What are concrete tasks to do? First of all, that's usual that we do already for all homework. It is described to describe initial state and all possible final states with zero energies. We do it for decay. We also do similar work to remind you when we do second order perturbation theory. The only point that in this case, these states are not final states, they're virtual states. Anyway, we are requested to give the states, and immediately, since we have trained quite a bit, we want to compute the matrix elements of dipole moment to compute the rate with golden rule. Here, the funny point is that this matrix element should involve this interesting state, which is characterized by two numbers A and B. Right. So after point A, we have rather abstract formula, squared of matrix element, delta function of energy, and summation over all possible modes. To make sense out of that, what do? We replace summation by integration, right? That is what you have to do in point B. Right, and we want to obtain the emission rate in a given direction for a given polarization direction. What does it mean? That the direction of the photon is fixed, but the magnitude of its wave vector is not, but it is subject to delta function constraints. So eventually we integrate delta function over the modulus of, what is that, K. Right. Then what to do is to look at the results and understand how the coefficients A and B and the angles determining the direction of Q, how do they interplay? Right, there are concrete questions to answer. Zero intensity for polarization 1, zero intensity for polarization 2, and zero total emission intensity. Give A, B, and the angles. Right. After that exercise, we do standard work. We just sum up all intensities to get the total rate. Good. ABC we solve this problem with Fermi-Golden rule formula. That will work also for atoms, which are not harmonic oscillators. Will work for any system. Now we're gonna be specific for this parabolic confinement quantum dot, which is oscillator by itself. Then we are supposed to do the following. So this Hamiltonian, which contains a quantum dot, interaction, and photons, we apply external force to the electron of the dot. Here it is. Then, since everything, all Hamiltonians are bosonic Hamiltonians, we can derive easily Heisenberg equations for these operators and solve them, because Heisenberg equations are linear. Yeah. And right, we solve them to find the following relation between force and average response, average deviation of the electron in x direction. So how do we call the coefficient? The coefficient between action and reaction is a susceptibility, frequency-dependent susceptibility. So in fact, we derive equation for susceptibility of this oscillator. If I look at these terms, they're pretty usual for an oscillator without interaction with environment. So if we skip interaction, we would end up with these terms. Those are due to interaction, and I could say they describe frequency-dependent friction which photons exert on this oscillator. Good. So you write equations, you solve it, you answer point E, and this is not a bonus question. I have to stress it. Fine. What else? The hint. Doing the last problem, we can forget about y direction. It doesn't involve any y direction. You could just concentrate on one set of bosons. And there are some hints for you to recall. Heisenberg equation and some summation formulas, including, well, integration of delta function. Fine, so let me go through the points again. We have a quantum dot, which is harmonic oscillator. Looks a bit unusual, but that can be easily done with parabolic confinement potential. And we look at dissipation in two ways. A, B, C. It's a standard application of Fermi-Golden rule formula. D, E is using the property of oscillators and deriving Heisenberg equations, interpreting it as friction. Fine. So I suggest that you think about this problem now, and we will answer your questions. Good, problem number 10. And yeah, it's about lasing. It's about lasing, which is a part of advanced of a course of advanced quantum mechanics. Whether lasing is a quantum phenomenon, well, it seemed to be a political issue. When I was a student of that time, all this laser technology is used to call quantum electronics from all word combinations. I couldn't recall why. Perhaps the reason was selling quantum, something unusual, which has to be propagated. So it was a fancy word combination for this, quantum electronics. A generation has passed and lasers don't have to be advertised anymore. They've been in every classroom, in every shop. And people understood that the word quantum just scared engineers. So there was a lack of qualified personnel in laser technologies. So there was an opposite way. And there will be a plenty of textbooks has appeared which plainly says lasers without quantum mechanics. Right, it was about the same, about the level, the lasers with the same equation, but the stress was opposite. Okay, it worked. So I guess most laser physicists do not care about quantum mechanics, except people who are really in research, in laser, in front-end laser research and in laser applications involving quantum mechanics are frequent. So it all depends on politics. Now our politics is such that we put it in the course of advanced quantum mechanics. What I wanted to stress that all equations which you would solve in this chapter are in fact classical. In this problem are in fact classical. Good. So we look at the simple model of laser. It's been in book and also in the lectures. So what are elements? There are atoms. We don't care about which atoms, which are pumped to excited state with the rate R. And there's natural decay to the ground state with the rate capital gamma. And in simple model of laser, you just have a single mode, single additional mode for stimulated emission. Now it's different, and there's infinitely many such modes. We study multi-mode laser. How to make multi-mode laser? It's pretty much the same method as in many lasers. You put two semi-transparent mirrors at two ends of the laser, and there is a sequence of what is called Fabry-Perot resonances. Okay. If the distance is large, you could pick up on the single resonance, but in principle, there's plenty of them. And this is the way, this is the situation of our particular laser. So there is a plenty of modes, and the emission rate without stimulation depends on mode number. Mode number M, it goes from minus infinity to plus infinity. So it has a maximum at K0. And in principle, this plane, M0. Kappa is a coefficient which is smaller than 1. Okay, so there are many modes. It happens so that, all these modes have similar frequency. We could disregard the frequency difference between them, and same quality factor. Good, and there's also total number of excited atoms, and X. Good, then to the tasks. As promised, the equations are classical. And the first task is to look an equation similar to that doesn't make any sense if you don't look at this equation. Let me show you that one. I stop this share and I will try to find this equation. Let's see. Must be somewhere. Oh, look, I found that. So what does it show? It is a question about number of photons in a mode. We have many modes, so we have separate equation for each mode. What does it have? Number of excited atoms. Each atom tries to add a photon, a photon to the mode with a coefficient gamma. Okay. So there's excitation of the mode with the rate proportional to number of excited atoms, and what is essential, the number of average particles stimulated in this case, emission. In addition to that, we have a damping term, so photons leave the laser mode, and it is characterized by quality factor of the laser. Fine, so this is an equation for balance. Average number of photons in the mode is determined in this way as a balance of emission from atoms and losses from the mode to empty space from the laser. Did you get this? Yeah. Okay, fine. So that was equation 994. Let me get back to the problem. No. That doesn't work. So now it's better. So derive an equation similar but different. What is the difference? You write it separately for each mode and you solve it. It's linear equation. It's easy to solve. All right, there is a task which actually introduces some NX max, some parameter which we will need faster way. Good. Now we would like to add another equation. That was equation for photons. We need an equation for atoms to find the actual equilibrium. So all logical, so let me switch to the book again. Let me find this question. Where is this? Homework. Oops. Here it is. So again, we have a balance equation. R is the rate with which a laser is excited. Like we put it into the electric circuit, there's electric discharge for the laser with some intensity, atoms are excited. And they lose their energy by decay in two ways. Natural decay is capital gamma, and the decay into laser modes. What's the difference? We have now many laser modes. We have to sum up over the modes. Yeah. So two balance equations, for photons and for atoms. Here we are. So now we have two questions, and we have to take them together to find the stationary state of the laser. There are different regimes. If excitation rate is small, it would hardly laze, right? The number of photons in the modes will be small. If you raise this threshold, it will. And the next is to present this equation in a compact form. Some students have a problem with this. They see it as a nuisance, while all these rescalings is to help you. Just to let you concentrate on the quantities which you really want. Good, so these rescaling quantities are, which shows the intensity with which energy which you supply to your laser, and A, which is more or less the result of the laser, how much atoms are excited in comparison with maximal value. All right, so there is an equation in the form to be derived. Good, then point D, and although it's mass, some people have problem with this. Right. Finally, it's a summation or things like that, which cannot be done analytically. If you sum up it over M, there will be some complex function. So we want to replace summation over modes by integration. And one has to figure out when it is possible. Right, so let's think about this. It's a pure mathematical skill, but it requires some thinking. Good, then one needs to solve it in two different limits, and one of the limits eventually expect to good lasing. And you see that from this phrase, R equals 1 is an approximate threshold of the lasing. There's also a bonus point. But it's kind of purely estimations. Do it if you want to understand the problem better. You might want, you might get some extra points for your reasoning. I don't think that this formula directly belongs to there, but it's useful formula. It would do no harm in any case. I guess it's just because we replace here summation by integration. Good, so that's a problem about laser. As I promised, all equations are classical. One just needs to solve them and understand how laser in multi-mode configuration, how does it work?